Welcome to the 13th presentation in the inaugural webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Camille Petit of Imperial College London. I'm Daniel Sidarius of NIST in the United States and the Secretary-Treasurer of the IAS. The other host of this webinar will be Arvind Rajendran of the University of Alberta. Questions to our speaker will be moderated by David Donacci of Imperial College London and Nicholas Wilkins of the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or of the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at the channel noted on screen for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. During today's webinar, questions can be submitted to the speaker via the Q&A tab of the Zoom client or as questions on YouTube, and those questions will be forwarded to the Zoom hosts. There will be a break for questions midway through the webinar and then again following the end of the presentation. Please help us evaluate this webinar series by taking the online survey at the bit.ly URL shown on screen. This link is also available on IAS Twitter and will be circulated via the IAS mailing list later today. We will use the survey results in planning for future webinar series and other IAS events online. I'm now pleased to introduce today's speaker. Dr. Camille Petit is a reader in materials engineering at Imperial College London. Her research focuses on the fundamentals of porous materials in terms of their formation, structure, and chemistry for applications in separations and solar fuel production. She also has interests in the integration between materials development and adsorption process engineering. She was recently recognized by the AICHE in its annual 35 Under 35 Award for Rising Young Scientists, and has received the Philip Leverhelm Prize for Engineering in 2019. Today, she will present on challenges in adsorbent development. And with that, I'm going to hand over screen control to Camille, and I hope you all enjoy today's presentation.
Okay, I'm going to share my screen.
And Camille, if you can also turn on the camera if you would like, yeah?
Let me just... where is the video? Here.
Perfect, looks good.
Oh, good, yeah?
Yep.
Okay, so good morning or afternoon, everyone. Thanks a lot for joining in. I hope you're all safe and healthy, and I hope also that the webinar series from the IAS has been a nice distraction given the current situation. I'd like to thank also Arvind, Dan, and Andreas for the invitation and for the smooth organization of the webinar series. So what I want to do today is tell you a little bit more about what goes into the mindset of a material scientist or a chemist when designing an adsorbent for a specific separation. And doing that, I would like to answer three questions. How can we design a highly performing adsorbent? How can we incorporate materials and process complexity? And how can we go beyond adsorption, taking advantage of the sophistication and complexity of some of our materials? You will see that there are some overlap between this webinar and the other webinars in the series, and I think it will highlight how there are connections between the different topics and also how multifaceted this challenge of designing an adsorbent is. This is not an exhaustive presentation. It gives you more of a general view as to how we go about designing an adsorbent. So I'll focus first on the first question: how can we design a highly performing adsorbent? And here we will look at 3 topics. How do we select metrics? How do we deal with numbers? And by numbers, I mean the number of possible structures that we have at our disposal, and how we should consider benchmarks and targets. And I will start with the first, which is selecting metrics. Before doing that, though, I'd like to just review briefly the different separation routes when we think about adsorption. So we have 3 of them: equilibrium separation, molecular sieving, and kinetic separation. When we look at equilibrium separation, here we are taking advantage of differences in intermolecular forces or adsorbent-adsorbate interactions between 2 species and the adsorbent here. If we consider molecular sieving, here we have 2 molecules that we want to separate of different sizes, and one that is able to penetrate inside the adsorbent pore versus the other cannot. And so we have separation based on size. And finally, we have kinetic separation. Here we are separating based on the difference in diffusion within the pores of 2 different molecules. And you will see that in the presentation today, I focus mostly on the first 2 types of separation. So as I said, we need to select metrics. And when you think of metrics, there are different kinds. And the first kind, I would say, is materials-based metrics. And we can think, for instance, of the uptake. So if we consider the graph at the bottom here on the left, we have an isotherm at 2 different temperatures. So it characterizes the amount of gas adsorbed as a function of pressure for 2 different temperatures. And the uptake would be the amount of materials you have adsorbed at a given pressure and temperature. We can then consider the working capacity, which would be the difference between the amount adsorbed and the amount desorbed for a given, again, temperature and pressure condition. We have then also to consider the selectivity. So when you want to separate 2 species, there is one that you hope will be adsorbed preferentially versus the other. That will characterize the selectivity. So if you look at the graph at the bottom right here, you see that the thick solid lines here are for CO2 versus the dotted lines here are for nitrogen. And so we have a preference towards CO2 adsorption, and so from that we can start calculating what is called the selectivity. And finally, we have the regenerability, which characterizes how much of the adsorbed amount can be recovered upon the cycle of adsorption and desorption. So all those materials-based metrics are somewhat linked to the chemistry and the structure of our adsorbent. So we have direct links to some extent between uptake, working capacity, selectivity, and regenerability, and surface area, pore size and shape and flexibility, chemistry and defects. So if we think, for instance, of porosity, we have here a series of metal organic frameworks, or MOFs, and you see that they have different pore size, different pore shape, and that will, of course, influence your adsorption process. If you look at chemistry, here we have, for instance, a view of a carbon-based material where we have different types of functional groups, whether they are nitrogen or oxygen containing groups. And you see that depending on that chemistry, you probably will have different types of interactions between the adsorbent and the adsorbates. We can also consider, for instance, that we might have defects. If we consider a crystalline adsorbent, there might be some defects in the form of, for instance, missing clusters, and this will also influence the chemistry of the material, but also the structure. You see that the porosity here changes in your material compared to a defect-free MOFs. So if we go into more details and look at examples of those different trends, we see here, for instance, the influence of the porosity on hydrogen uptake or hydrogen storage on carbon sample on the left and MOF sample on the right. And you see that as we increase the surface area, we increase the uptake of hydrogen, which is a common trend observed for hydrogen storage. If we look now at the effect of pore size, I take here the example of a titanosilicate molecular sieve, which has the particular property of changing its pore size in a way, depending on the activation temperature. So you see, as we rise the activation temperature, we have some changes in the pore size. And you look here at the distance between the silicon and oxygen atoms, and you see that we have a decrease upon increasing the temperature. And that can be helpful when you want to separate molecules that are somewhat different in size. And so you see here that we can separate ethane from methane, or methane from nitrogen, and nitrogen from oxygen, even though the difference between the size of those different molecules is relatively small. So it's a nice example of a molecular sieving separation process. If we look at the effect of chemistry, I take here the example of a MOF, which is called MOF 74. It has unsaturated metal sites, which means that those metal sites that you see here can coordinate with some adsorbate, in our case here, CO. And so depending on the metal that you use for your MOF, you will have different strengths of interaction. And you can see that here with the heat of adsorption, that will change depending on the metal that you use. And this is related here to the distance between the metal and the CO molecule. And that can be taken as an advantage for CO-nitrogen separation. You have more example of how to take advantage of that chemistry in the webinar by Philippe Lerouillet. I wanted to also give an example of the effect of defects that happens a lot, for instance, in MOFs, and I take here the case of UIO 66, which is a zirconium-based MOF. We have here the structure of UIO 66, and we have here a missing linker. And you can see that because of that, that will change depending on what the missing linker is replaced by, and you have different examples here. We will have different heat of adsorption for CO2. So the black line here corresponds to the defect-free MOF, and then the others correspond to the defective, in a way, MOFs. And depending on the group or chemical you have attached here, you will have different heat of adsorption. And that will also show in your water isotherms here. This is somewhat confirmed if we, instead of having a missing linker, we have for the same MOF here, a missing cluster. We will have a change in the porosity, and that is what you see here with that nitrogen, the nitrogen sorption isotherms. We have a change in the porosity, and we also have a change in the heat of adsorption, which is for CO2 here. So basically, you see that we have, by changing either the structure or the porosity or the chemistry, we will have an impact on those materials-based metrics that I was mentioning earlier. But this is not that simple, in the sense that we may have tensions between materials metrics and those properties. And I take the example here of CO2 nitrogen separation using MOFs. So we have here isotherms for CO2 and nitrogen for two MOFs, MOF 74 and UTSA 16. Where we have the solid line, the CO2 isotherm, and the dotted line, the nitrogen isotherm for both cases. And you can see that for MOF 74, we have a good uptake of CO2, better than in the case of UTSA 16. But we also have for MOF 74 a greater nitrogen uptake, which is a negative thing if we don't want to end up with nitrogen in our outlet stream. And so we will have to basically balance between that CO2 uptake and nitrogen uptake, something that Arvin last week referred to in his webinars as well. So you see here that this is not direct connection between a better chemistry or better porosity with a given metric, materials-based metric. Similarly here, if I take different isotherms for different adsorbents, you see that, for instance, the blue curve here has a very sharp uptake at low pressure, and actually has the highest uptake. But that probably means that we will have to use a lot of vacuum in order to regenerate our material, which from a process point of view is not desired. However, if I take that black curve here, we have a lower uptake, especially at lower pressure, but we will not have to pull as much vacuum as in the case of the blue curve to retrieve the material adsorbed. So again, here you see that we have a balance to make. And so in fact, you could envision that as a potential optimization challenge between all those materials-based metrics here and the materials properties on the right, because they're all interconnected. In addition to that, you have to consider the process-based metrics. So that's another added layer in terms of challenge in a way. So imagine, look at the graph at the bottom here, you're feeding a mixture that contains molecule A and molecule B, and you want to retrieve molecule A, right? And so you will want to know at the end how pure A is, so that will relate to the purity, and how much of the initial amount of A you've recovered at the end. And also you want to know how much energy you had to use in order to get the purity and recovery level for A that you wanted. So in essence, you have adsorbent properties, so the materials-based properties, so uptake, working capacity, selectivity, regenerability, many adsorbents. And for each of them, you will have to consider potential operating condition in cycle, so temperature, pressure, and the cycle design. So for each adsorbent, in theory, you have to test all the potential cycles or conditions that you need. So that end up being a complete optimization challenge in order to get the best adsorbent plus process. So it's a combination of the two that gives you the desired recovery and purity for a specific energy consumption. And so I invite you to watch, if you haven't done so already, the webinar by Arvind last week that explained this in more details. But I wanted to highlight here that indeed for each adsorbent, and there are many of them, you will have a number of cycles to consider. Now, if you want to have a quick view and a quick indication as to how your adsorbent should look like, you can potentially use what is called shortcut models, and I give here 2 examples of them to check, in a way, to reverse engineer how the material should look like in order to get the desired recovery, purity, and energy. So you start from your process, you input, in a way, what is the target that you want in terms of recovery and purity, and that might give you some idea about how your materials look like. And that is, again, you can have a bit of more explanation of the shortcut models from Arvind's webinar. That's what we did here in terms of reverse engineering, trying to identify what are the materials properties that will give you desired target in terms of CO2 purity and CO2 recovery in the context of CO2 nitrogen separation for different types of industries, so natural gas, coal, cement, and steel. And what you can see here is that you have different color codes. So as we increase the purity, it becomes more red, and as you increase the recovery, it becomes more red. And on those different axes, you have the heat of adsorption for nitrogen, the maximum uptake, and the heat of adsorption for CO2. And all those parameters are linked to the isotherms for a given materials. So you can extract, or you can, if you have your materials isotherm, you can see how they would compare to the values shown here, and whether you are in a region of purity and recovery that is, in a way, in the right zone.
So that's what I wanted to say in terms of looking at metrics and showing that this is indeed not only a materials-based problem, but you also have to look at the process aspects. Now, you also have to consider, as I said before, that you're going to have loads of potential adsorbents. So you're going to have to deal with a lot of numbers. And so if you consider, for instance, metal organic frameworks, which is a type of crystalline adsorbent, you have a number of databases, for instance, the Cambridge Structural Database, or the core MOF database here. And from those databases, you will be able to do a screening of the structure, because you will be able to do molecular simulation for all those existing structure. And I invite you to look to watch this webinar by Randy Snur as well. This kind of database also exists for zeolites. And so you can do that same kind of screening exercise with zeolite. And this is what has been done here, for instance, in the case of methane uptake for dilute streams, where we have here the amount of methane adsorbed for different types, many kinds of zeolite structure, either the IZA zeolite or predicted zeolite structure. And you can start to see where the ones are that would give you the desired uptake, for instance. Right. Even though the molecular simulation allow you to, in a way, narrow down the number of promising structures for a given separation, there might still be a lot of potential structure which you have to check. And that's when experimental screening becomes useful as well, where you can use, for instance, platform like the one presented, manufactured by ChemSpeed, where you are able to synthesize a number of potential structures that you would have defined from your computational screening. The problem becomes a little bit more complex when we move from crystalline structure, which is the case of many MOFs and zeolites, to amorphous structures, if we think, for instance, of carbon-based structure or glassy MOFs, where here we don't have a well-defined geometry for our materials, and so those screening exercises become much more difficult, and the reverse engineering approach I was discussing earlier might be a useful tool to get a sense as to what amorphous structure might be interesting. Now, I want to say a few words only on considering benchmarks and targets. So you have to ask yourself for each separation that you are targeting and each materials that you want to develop, what are we trying to replace? What is the best technology out there to do that separation? And what is its performance and cost? Because that will give you some targets to potentially surpass. And what are the specifications? So if we take, for instance, the example of CO2 capture, we have an existing technology, which is the amine scrubbing. And so that gives you some guidelines. And in terms of targets and specification, you have the DOE targets. You could, for instance, consider the energy required or the cost or carbon price as a target as well. So it's always good to keep in mind what is out there, if there is an existing technology, and that kind of puts a barrier that one has to overcome. And not forget that. And if I also add something here, if we take into account CO2 capture, of course, you could also compare as an adsorbent to zeolite 13X, which is a commercial porous materials. So I'll stop here for now and take any questions.
Thank you, Camille, for your interesting talk so far. We'll just wait a few minutes to get any questions to come through.
Camille, this is Arvind. While the questions would come in, I have a question. If, for example, in your screening, you find a structure that is very good from, let's say, from one of these structural databases, and then if you want to go into the lab and synthesize these materials, what are the challenges that you see in doing that?
Right, so a number. The first one is if I take the example of metal organic frameworks, which is something that we work with in the lab, is whether, for instance, the organic linker is something that is commercially available, or whether that is something that will have to be derived from another organic molecule. So that would be the first step. Of course, that is an extra challenge if that's not already available, and that will also pose a challenge from the scale-up perspective if that is not commercially available. And the other aspect is in terms of conditions for the synthesis. So if that particular structure has not been reported as synthesized before, one will have to come up with a synthesis method to produce it, and that means a range of potential conditions, and that's when the high throughput process or screening of condition can be quite useful.
So just to further clarify, when you do the high throughput synthesis, what conditions are typically variable? What do you typically start with?
So we don't have a high throughput system in our lab, but I can speak more generally and say that you'll have to consider what type of solvent, the different ratios between the different reactants, whether you use, for instance, modulating agents or not. So it's a matter of what chemicals, how much, in what concentration, and maybe play, for instance, with pH or temperature.
Good, thank you. David, if we don't have questions, maybe we move on and then we wait till the end.
Sure, that's what it seems like at the moment. So please, Camille, if you could continue on the presentation.
Right. So now I want to move on to the next question, which is how can we incorporate materials and process complexity? And I will clarify a bit what I mean here. If we want to really understand how the materials work, we need to understand how it works in situ, so in actual conditions. And also, we have to take into account the process complexity, meaning the gas streams that you're dealing with may not be only 2 molecules, but more than that. And so one will have to consider that if we want to test materials properly. So I will focus first on the in situ behavior. In terms of, for instance, in situ characterization of flexible MOF that has been nicely shown in the webinar by Stephen Haskell last week. So I refer you to that as well. I'll show here some example of techniques, so different techniques that have been used to really understand the mechanisms of adsorption in different materials. So I take, for instance, here the example of energy dispersive XRD, so X-ray diffraction, where here you're using a polychromatic light, and this is done at a fixed angle. And what you will see is, what you will monitor is the change of the structure. So I take here the example of MIL 53 upon adsorption of different heterocycle that contain nitrogen and sulfur. And if you consider first the map on the left here, we have the energy here and the time here, and you see that the color map will change, and the number that you see here corresponds to the Miller indices. So in a way, they give you an idea about the structure's evolution of the material. And the graph here on the right is, if you want, a slice of that, and you see that depending on the status of the adsorption, we will have different shape or different types of indices being shown. And that is an indication of a change again in the structure that you can monitor really in situ, so in real time. here I take the example of neutron diffraction. And the advantage of neutron diffraction is that it will be able to look at very light elements, unlike X-ray diffraction. So here that technique has been used a lot, for instance, to monitor hydrogen adsorption in MOFs. And I take here the example of MIL53. So if you look at the graph A, for instance, you have different patterns, whether the MOF is empty, so activated, or whether we have started the adsorption of hydrogen. And if you look at B here, that's a Fourier transform map in a way, where we can start to see the progressive adsorption of hydrogen within the pores of the MOF. And the hydrogen is what you see in yellow here. And the graph C here shows you the Rietveld refinement, where we have actual location of the hydrogen atoms within the structure upon adsorption. And in D here, so that will be, if you look at the y-axis here, a time evolution. And again, it's a map, so the color indicates the intensity of certain peaks. And what you can see here is that if I take, for instance, the example of that peak here, we have a shift and then a return to the original position. And that pattern here is indicating a progressive adsorption and then desorption. So we're showing here, or we're seeing here, a reversible adsorption of hydrogen within the structure. If we take, for instance, another technique, which is X-ray absorption spectroscopy. So here we're monitoring the chemical nature, or the chemical environment of atoms. So we take here the example of a CO uptake on a copper impregnated MOF, which is MOF 74. And we wanted to know first what was the nature of the copper atoms within the MOF, impregnated within the MOF 74. And if you look at the graph on the left here, you see a decrease of the copper 2+ peak upon activation. So those lines here correspond to different types of activation. And so you see that you're decreasing your amount of copper 2+ and increasing here your amount of copper 1+, which is the desired form if you want to have preferential interactions with CO for the adsorption. And the graph here on the right shows similarly the evolution of copper 1+ and copper 2+ upon adsorption of first nitrogen and then a mixture of CO and nitrogen, then fully CO. And what you can see here is that we have a decrease in the intensity of the peak corresponding to copper 1+, which is an indication of the interactions between CO and copper 1+. Another technique here is that of in situ drift spectroscopy. And I give here the example of SO2 adsorption on a given MOF, which is called NOT 202A. And in situ drift is a common technique used to look at solid or powders formed in different atmosphere. Okay, and so at the top here, you have, in a way, you're monitoring for different pressure of SO2, how the spectrum looks like. And now you're introducing in the middle panel here, the MOF, and you see that there is a difference because we have specific bands related to SO2 adsorbed in that specific MOF. And if you subtract the first spectra here, you'll get the bottom one here that gives you, in a way, increasing intensity and increasing area of those peaks related to SO2 for different pressure. And from that, you can start building an isotherm for that specific SO2 adsorption in that specific MOF. I wanted to also highlight the power in a way of in situ NMR spectroscopy. Here in the case of water adsorption on a very common MOF, which is HCAST1. HCAST1 has, as MOF 74, which I mentioned earlier, unsaturated metal site here, so they can interact with a lot of adsorbent, and in particular water. And if you look at the NMR spectra of the dehydrated sample, it's very different from the one that is hydrated. And you can see that depending on the form of water molecules in that material, you'll have different shift for that NMR peak. And you can therefore distinguish between the different types of water in that MOF. Another example here of the use of NMR spectroscopy, it's a more recent work here where we look at the CO2 diffusion in MOFs. And here, if this was done in the case of MOF 74, which has in a way those one-dimensional channel, and it's looking at two types of diffusion, so the self-diffusion of CO2 within the channels and across different channels in a way. And depending on the orientation of the MOF crystallite and the typical diffusion of CO2 within the pores and across the pores, there will be different signal for CO2. And so as the pressure of CO2 in the system is increased, you'll have different pattern for that NMR, carbon-13 NMR peak, which can be in a way used to extract the information on the diffusivity of CO2 within those channels. And that was published in those two papers by Alexander Force here. In terms of, so that's what I wanted to show in terms of materials complexity, and that there is really a challenge in looking at how the materials behave in real condition and live. And now I want to focus on, in a way, the conditions. So as I said, a lot of the screening of the material is done in ideal condition, where we look at simple mixtures, for instance, of two species. But of course, real conditions are more complex than that. They contain a number of components, and one that is particularly often present is water. And when you think of water, you want to consider two aspects. You want to ensure that your material is stable, and you will also want to ensure that water will not compete for adsorption with your desired adsorbent. And water stability may not be an issue for many materials, but for other it is, and it can be the case, for instance, for MOFs. And in that review paper here, they highlight different strategies that have been used in order to ensure the proper stability of MOFs under presence of moisture. So it can be looking at the strength between ensuring that there is a strong bond in a way between the metal and the organic linker. It can make sure that there is steric hindrance around the metal site, because that's in a way the weak point. It can also prevent, in a way, clustering of water again around that weak point, or make the material more hydrophobic, for instance, using carbon coating, or functionalizing the ligand with a hydrophobic component. Assuming the materials is water stable, you now have to consider whether you'll have a competition between water and your desired adsorbate. And here is the example of a study done looking at CO2 uptake in the presence of water. And that study considered in a way an extreme scenario, in the sense that the materials were exposed to water first, and then CO2 uptake was measured. And that was done for a number of materials, many MOFs, and also some carbon and zeolite. And what you can see here is that for some materials, the water will not affect much the CO2 uptake. However, for others, like especially the one here at the bottom, you'll have a dramatic decrease in the uptake. And so that is something that, of course, needs to be taken into account. If we think about CO2 capture, water is present in non-negligible quantities. That will be important. Going beyond that, you want to mimic real conditions. And so ideally, you want to expose your material when you test it to real mixture of gases in that case. So here, that was done using this setup at Berkeley, where they had a mixture of components of CO2, nitrogen, and water, and they could see how the performance changed, whether they were considering pure CO2, which are the green bars here, and the multi-component stream. And again, for some material, this didn't make much of a difference, but for others, you can see a dramatic decrease. And that is, for instance, the case of MOF 74, which is this one, or zeolite X, which is famous for absorbing a lot of water. So as we want to really test those materials, we want to really mimic those real conditions and introduce as many impurities as is realistic, as is the case in real life, because some of those impurities, can, even if they are in small quantities, can have a dramatic impact on your performance. In addition to looking at those different components, you have to do dynamic tests. You have to then start to look at small scale TSA, PSA, PTSA setup. And I invite you to watch the webinars of Andreas, Stefano, Enzo, and Farouk and Nick to have more insight on those other issues that needs to be taken into account when you want to really move towards real conditions. I want to now move to the last, brief last part of my presentation, which is how can we go beyond adsorption? We have to understand that the materials that are at our disposal are quite complex, and some of them can be nicely tuned in terms of their structure and or chemistry. And therefore, one can think that we can do something else than adsorption with it. And if you consider a typical separation process, you have your inlet stream, which you want to treat, and for instance, you want to separate your chemicals, and that will then end up with your desired outlet and some other outlet stream, which your not desired compound. And those chemicals that you separate, probably either you will use them as they are, or you will use them for instance, catalysis. And so that means that between the separation step and the catalytic step, you have a regeneration step where you're basically regenerating your adsorbent. So the question becomes, can we actually do something that is combined? Can you combine the separation and the catalytic steps such that you avoid, in a way, that regeneration step, or in other words, the regeneration step is used to trigger the catalytic reaction, because that will save that intermediate here. This is something that in our group we've been quite interested in, looking at, for instance, CO2 capture and conversion, and we've done that for different types of systems, whether they were based on crystalline materials like MOFs, or they were based on porous, on amorphous system, like for instance, boron nitride. Other groups have looked at this as well, and I take here the example of the adsorption and detoxification of a chemical warfare agents. So here they've used a zirconium MOF, which also contain porphyrin units as ligands here, and this MOF has been used not only for the adsorption of those toxic compounds, but also upon irradiation with lead, they were able to convert it to safer chemicals. So here we are integrating the adsorption step and the catalytic step for detoxificating those chemical warfare agents, all within the same structure. So the chemistry that was in a way beneficial for the adsorption is also beneficial for the catalytic step. This is also shown here in this work here on carbon-based materials, which they've used those materials for phenol adsorption and conversions to catechol. This is the short reaction here. And under solar irradiation, those carbon-based materials have been able to adsorb the phenol, and those sulfur-containing groups were in a way key in the adsorption process, but also key in the conversion process towards the catechol chemical. So here again, we have a porous materials that is able to not only adsorb phenol or adsorb the chemical of interest, but also catalyze its conversion to a different chemical. And you see here the use of light. So in a way, in all the examples that I've shown, and for the CO2 work as well that we do in our work, the trigger is light for that catalytic aspect. So in a way, that's all I wanted to say for today, and to, in a way, just generally show you how we want to make adsorbent work for a complex world, where we want to understand and incorporate performance targets, so not only considering the materials-based metric, but also the process-based metrics, and how it's key to incorporate them all, and how there's an extra challenge when we think of materials that do not belong to a database and are more complex and more disordered in their nature. We want to understand adsorbent life, and that's what I refer when I mean looking at in situ analysis of the adsorption process and under live conditions. So we want to make sure that we test the materials in conditions that are relevant to the full scale setup. We want to be able to exploit complementary features and of those materials, and to make bifunctional materials, so they can be used not only as adsorbent, but something else in addition, in a way to maybe intensify processes. Something that I haven't looked at today is we want to make sure that materials we will be able to manufacture ready-to-use adsorbent, and this is a topic that was discussed by Fatemeh earlier in the webinar series. And we also want to make sure that those adsorbents are made from sustainable resources. Something that I haven't referred to, but of course, one wants to make sure that it doesn't contain rare earth metal, for instance, or that the solvent used in the synthesis are greener solvent. All those issues need to be also considered in order to make the adsorbent. So that's in a way the key messages I wanted to pass on today. Some of the references I wanted to highlight. The first one is more for general reading, and that is the report, the latest report on separation that was produced by the National Academy of Sciences, Engineering and Medicine. It's a very recent report. It's not only on adsorption, it's more general on separation sciences, but a lot of the conclusions or direction that are provided here apply, I think, to the adsorption field, and I think that that is a nice read. In terms of the other references, I wanted to list some that are more engineering and some that are more science-like. So these two here are the shortcut models I was referring to earlier that can be used in a way for reverse engineering of adsorbent. And the last two here are two books that really look at the characterization of adsorbent, whether they are more amorphous, like the first one, looking specifically at activated carbon, or the second one that looks more at metal organic frameworks, so crystalline-based materials. So that's all for today. I thank you all for your attention, and I'd be happy to take any questions.
Thank you very much, Camille, for your lovely talk and summarizing these kind of multifaceted aspects of adsorption. We've had a couple of questions come through related to the first part of the talk. So the first one of those is from Shrinu Banoth, who says, nice presentation, and they would like to know how many MOFs have so far been commercialized for post-combustion CO2 capture?
So as far as I know, and none commercialized for CO2 capture. The only materials that I can think of as adsorbent for CO2 capture are the one used for direct air capture. But I think for large-scale CO2 capture, the commercial route is still the amine-based technology.
Thank you. The next one is from João Marreiros, who wants to know what the applicability of kind of mixed ligand MOFs would be for gas separation and storage, and how do you address the linker distribution impact on structure-property relationships?
Right. Can you repeat briefly the first part of the question?
What do you think the applicability of mixed linker strategies in MOF synthesis for gas separation and storage?
Right.
Is the direct question.
Yeah, I would say why not? As long as one can, that you're not shooting in the dark in a way. So if you need again to look at the targets, and can you potentially screen the performance of all your mixed phase linker MOFs to get a view of their capability before trying to synthesize them. That would be because, of course, you probably will have different combinations of potential mixtures of ligands, and that will end up being quite a lot. And in terms of experimental work, so you probably want to narrow down that work and do some screening and simulation beforehand to see which one is a potentially interesting structure. Also considering that whether those linkers are very exotic linker or not, because in the context of CO2 capture, we're dealing with a very large scale issue. So those materials, we have to be prepared in a very, very large scale, and that in a way relates to the question from the first person. And the second part of the question, David, was?
The second part was, how does the linker distribution impact on the relationship between the structure and the kind of adsorption properties? Right.
That's a bit beyond what I know, but I would say a priori, you're going to have, very generally a change in shape, and depending on the chemistry of your linker, a change in chemistry as well. So both aspects will influence your uptake, unless there is a very big change in the size of your linkers. Maybe the first impact will be on the chemistry, on the chemical aspects from the adsorption point of view.
Right, thank you. You've touched on scale just before in your previous answer, and we have a question from Arvind relating to that, and he would like to know what some of the challenges are in scaling up MOFs and structuring them to the kilogram scale.
Right. So scale, you have to look, I think, at from a more of a LCA point of view in terms of the greenness of the process and of the chemicals being used. And also whether you're dealing with a batch versus a flow process, the flow chemistry being favorable. At the moment, none, apart from BASF at some point, but not anymore, none of the big chemical companies have, in a way, pushed for the upscaling of MOF synthesis. So everything has been done by startups, and many of them have been mentioned in the webinar by Philippe Llewellyn. And so, in a way, it's yeah, again, not a big chemical company pushing for that at the moment. And so first you want to indeed produce the MOF at scale. And then second is, as Arvid was mentioning, is you want to shape them. And there are different ways to do that, whether you go more for beads or pellets. And what becomes difficult in some of, for instance, the metal organic frameworks is the mechanical stability. And so ensuring that this is high enough and this is maintained upon structuring is not easy, and that's something that Fatime earlier as well alluded to in her presentation. So greenness and I would say mechanical stability are quite important, assuming that all the chemical infrastructure for the upscaling is in place, which is existing in chemical companies.
Right, thank you. We have a comment from Stefano Brandani relating to the kind of multi-component adsorption you referred to in one of your slides. And he says, all hydrophilic materials are similar to 13X when water is added. Process regeneration is countercurrent and breakthrough curves are co-current. So care should be used in inferring the effect on a CO2 capture process.
Yeah, that's true. So some, probably some tests are quick tests, but yes, you have to consider the final cycle in a way. Yeah.
Right, thank you. Our next one is from Arashdeep Singh, and they would like to know what factors are considered in developing adsorbents, zeolites and MOFs for multi-component gas separations, for example, hydrogen from syngas.
Sorry, what was the beginning of the question?
What factors do you have to consider when developing an adsorbent for multi-component separations?
Right. So you have to, ideally, you want to be able to test your material within considering the actual mixture, right? This is not easily done, and sometimes the setup is not available. So one would go about doing that in a simplified way by looking at uptake or adsorption, desorption behavior for the single species, and then maybe move on to breakthrough tests, considering potentially binary system. But ideally, you want to have what I was showing earlier, which is the setup, for instance, with that was done at Berkeley with water, nitrogen, CO2. That was under equilibrium condition, but having that full mixture. But if that is not available, one would go towards a single component first and looking at selectivity based on those pure isotherms. Right,
thank you very much. And our last question for the moment is from Angel Hojati, and they are asking whether there is a correlation between pore volume and surface area. In some cases, the pore volume increases as the surface area decreases, and they say it is a bit counterintuitive.
that the pore volume increases as
Yes, so basically, an inverse relationship between pore volume and surface area is what they are asking about.
So that will depend on the material. So if you think, for instance, of metal organic frameworks, they will be really full of void space, and the actual surfaces is in a way not much, but the pore volume is large. If you think about more the carbon structures, because of the graphene sheet, which is something that Camille was referring to, you have really an actual surface, but the volume may not necessarily be larger. So it will depend on the materials that you have, and in a way the density of atoms within your structure.
Right, thank you. That appears to be all the questions for now. And if there are no further questions, I will thank you for your presentation again. It was very lovely. And I think we are now passing back over to Arvind to finalize the webinar.
Excellent. Camille, if you could just stop sharing your screen for a moment. Yep. I will bring up mine. Let me just share my screen here. Just a moment. Okay, so thank you so much, Camille, for this wonderful overview of the challenges that we encounter in making adsorbents. And with that, we come to the end of the first series, the first webinar series offered by the International Adsorption Society. We thank all the speakers and the listeners for tuning in. These talks will be uploaded on YouTube, and we've already provided you the link to the YouTube. It's the same place where you watch the live stream. I would also request you to take a moment to submit your feedback at this address that is shown on your screen. And you can also subscribe to our mailing list without having to be a member to know about IAS activities. And I would just request you to visit our website. With that, we close today's webinar, and I wish you all a nice week ahead, both safe and healthy. Thank you.